So this session um, is um, is a lecture on Introduction to EBSD, where Mike and Sarah asked if we could present something like this because of some of the new users and so forth, to give an introduction to the acquisition technique and the software analysis, and present equipment and capability here in Manchester, and familiarize our EBSD community with other users. So the aim is to raise the level of EBSD knowledge amongst our members, and discuss how EBSD users can keep in touch as well. So I am, if you don't know me, I'm Ali Golinia, a research fellow at the Department of Materials and the Electron Microscopy Center, and I work on materials characterization. That's what I'm interested in, especially on combined with phase analysis in SEM, focused ion beam, and EBSD, and which we'll explain in this session. Also, I am interested in 3D correlative microscopy, so combining all this with serial sectioning and comparing it with X-ray tomography. And another interest of mine is linking these microstructures to mechanical properties, such as in situ tensile deformation in SEM. So my co-presenter is Jack, so I'd ask him to present himself and introduce himself to the audience, please.
Thank you, Ali. My name's Jack Donoghue. I'm an experimental officer here at the University of Manchester, and I look after a number of systems which have EBSD, a number of the more specialist ones in general, so the in situ testing microscopes, laser plasma fib, and this one behind me, which is the high throughput SEM, which I'll show off some nice examples of in a little bit. But yeah, so back to you, Ali, for the moment of it.
Thank you, Jack. Maybe Michael, if you want to give a few words about yourself and also this session, why it came about, would that be okay?
Fine, yeah. Thanks, Ali. Yeah, my name's Michael Faulkner. I'm the Electron Microscopy lead for the platform, which covers Jack's area, which is PSI, Earth Sciences, NGI, and MECD, which we're just moving into. And it's become apparent that with the move, we've not been able to keep up with training at such a great level. And EBSD is one of those areas where I thought it would be a good idea to get everybody up to a certain level and a certain understanding. So we can move from there. And Ali, thankfully, agreed to do this, and Jack as well. So thank you to you for doing this.
Okay, thank you very much. So without ado, we'll start. So I'm going to just share my screen. So I'll start off, and then Jack will follow on after me. So I'd like to just say that this is, so we have this is a part of University of Manchester EBSD users group meeting as well. That's what we regard it as. We have a format which I'll explain a little bit, which will be hopefully useful for our users, and take it from there. But in that, in this talk, what we'll cover is this: what's the EBSD community in Manchester, and then I'll introduce a bit of background about EBSD, and then Jack will follow up with the capability that we have. EBSD capability that we have at Manchester, and then we'll try and finish with some question and answer session. If you can then ask your questions then. So a bit, I know this slide is a bit text heavy, but I just wanted to give a bit of background about our users group meetings if you're not familiar with them. We started them together, myself, Jack, and Al Lake. Where during the COVID, there was hardly any, when we were locked down, things to do. So we started this thing going, and we're continuing it, where we have members from Department of Materials, but also across the university, and also other universities too abroad. You can join as a member to keep to be in touch with whatever is going on through a Google form, and then we keep you updated through our website, Slack site, and email. And also there is a subgroup with AZtec subgroup which meet within this format separately, and they're quite active to use it as an alternative EBSD analysis tool. There's also a M3 Coffee Club where people meet in a very relaxed environment and talk about their projects and instruments and sample preparation and research and so forth. And this is organized by Alex Davis, and the next one is actually tomorrow at 11 at Royce Hub Building, mezzanine. So you're welcome to attend that. Now, to get information about how to join, all the links are on our website, which is at the bottom here, microscopy.manchester.ac.uk/EBSD, where you can see the past presentations. So, for example, I gave an introduction to EBSD with a lot more detail about the specific parts of EBSD, which is recorded and is available on Slack. If you join, you can access those, as well as we have a multitude of other presenters that have given presentations from across the world, actually, I must admit. It's quite a valuable set of videos that you can download and watch. And also we have some training videos which we prepared, which we will do as well in the near future. So there's one on large area EBSD which we'll confirm future. So there are links here to join via the links here for this Google form, as well as the Slack site, and yeah, other kinds of information there all available to see. And the other thing is this, I just wanted to give you briefly about the Slack site. So here people discuss their topics and share their experiences and ask their questions. So we have channels for example, the AZtec there, but also coordinate systems, for example, users group files, meeting files, sample preparation. People send in their questions, how can I install this software, and so forth. And we try to answer it. And if you have further questions or you want more details, you can ask either Alec, Jack, or myself about this. So to start off, I just want to give a brief background about EBSD, which is EBSD stands for Electron Backscatter Diffraction. It's an SEM-based technique to measure crystal orientations, and it's applicable to crystalline materials in theory, because, well, you can sort of deduce something about amorphous materials so that they're not crystalline, but some crystalline materials are so fine that maybe the beam interaction volume is so large compared to the grain size that it can seem amorphous. So therefore, they may be crystalline, but EBSD may not be able to resolve it. But where it's within its capability, it's associated with that. And then it also provides absolute crystal orientation, and it's in submicron resolution. It's a useful tool also for discriminating between phases. So electron backscatter diffraction is EBSD, but also some terms are being used which do sometimes make it a bit difficult to interpret, but so I wanted to put these in there. So the EBSP is basically referred to mainly the patterns instead of the technique. Is in the past, in the early days, actually the technique was referred to as BKD, as backscatter Kikuchi diffraction, but that term is less used these days. But TKD is a new phrase that's relatively new, that's come about, which is more often used, transmission Kikuchi diffraction, which I'll explain briefly about as well. And then there are some commercial names which people tend to use, but not aware that these are actually not scientific terms. They're commercial names, such as OM, ACOM, OIM. So you need to be careful when you're using these in your publications interchangeably. So just to give a background, I was talking to Jack about this, and he thought it would be nice to have a bit of a history of EBSD, and I agree with it. So I've prepared a few slides for that. Just briefly, of course, this all started with J.J. Thomson discovering the electron in 1897, and then his son captured some actually realized diffraction of electrons, but it was Kikuchi, the year after, actually, G.P. Thomson, that actually explained what the pattern was about, and he presented this in a Nature paper in 1928, showing a pattern from mica. It's a mineral. And then later, actually in 1937, von Borsch extended Kikuchi's work and gave a bit more explanation how it all happens. And then Allen et al. In 1954 actually put a film into an SEM and captured the backscatter pattern from lead sulfide and other cleaved samples. But this, the one shown here is of lead sulfide. You can see a huge capture angle, and it's on a, basically put it in a film in there, snapped one, and then it had to open the chamber and take it out and develop it. So it's not an easy task to do something like this. And then Venables et al. Observed these EBSPs using a fluorescent screen where the electrons would hit the screen and then create light, and then that was captured on a closed circuit television camera. These patterns took a whole day to capture, maybe the film days, because the guy had to go and develop the film, right? So this was just one pattern, not even indexed, just, yeah, we can see a diffraction pattern, we don't know the orientation. Then Dingley and Schmidt tried to commercialize these techniques initially for ECP, channeling patterns, and then also for EBSD, using TV cameras. And this was basically a very manual affair. So you would use the camera to capture, and then you would manually detect the bands, and then the software would index. Actually, Dingley's one, you had to actually say which zone axes were which before it found the orientation, whereas Schmidt's method from the start, it was to define the bands to index the pattern. So this was a very manual and very slow, maybe one pattern a few minutes. And then in 1990s, Hopf band detection came about. So Krieger Larsen realized that he could convert the pattern to a different space called Hopf space, and convert the bands into spots. So it's usually very difficult to write a software to detect bands in an image, but spots, it can do that. So by converting the lines into a spot, so each line here would be a spot in the Hopf space, you would get you get a spot, and then the software detects these, and then knows where the bands are, and then compares it to the indexing, the match unit, reflector list, and index of it. So that created automation, which was at that time with the old detectors, maybe 1 pattern a second, and this was quite really speed. When we got this, I remember it was a huge thing because until then you had to draw the bands. So if you got 10, 20 measurements a day, it was really achievement. But with this, we could leave the system untouched, and it would go ahead and do these. So we could really get 1 pattern a second. And then CCT detectors came about where they were 25 hertz. So that increased our speed 25-fold, and that was a huge sort of step forward. And then in the 2000s, early 2000s, EDS integration came. So we could do it at the same time, in situ EBSD, because the speed was being high enough to do some in situ analysis, and 3D EBSD, because FIBs were coming about, focused ion beams. And then faster CCD detectors came about, where speeds increased to 1,000 hertz or so. And then CMOS cameras came in 2010s, where they really pushed the speeds higher up to right now we can achieve over 4,000 hertz on a very simple alloy submit, for example, single phase and large grain. But still, it is a capability that wasn't there before. So it requires some quality of pattern to obviously work, therefore, only in certain conditions, but it's there for us to use. Then this is a pattern that I want to show of a iron chromium intermetallic, where you can see typical bands here, and this is a zone axis in the middle here, where these planes meet, and we get a point. Actually, from crystallography, the bands are used for the indexing. The zone axes aren't, as opposed to how people thought initially that they were the important bits, points in the pattern. But one aspect to think about is that these bands are actually physical extension from the sample. So if you were an electron, you were sitting on the specimen, hit the specimen, and then you went to the detector, you would actually follow these lines. So these lines are formed by in real space, so to speak. So that, in that respect, actually, EBSD is quite a simple technique, as opposed to, for example, diffraction in TM, where you've seen the spot patterns are in a reciprocal space and sometimes not so easy to understand. But this is in physical space, so it should be easier to comprehend. EBSD performance is, I've noted down a few here. So it's a surface analysis technique, and I'll explain why. And its spatial resolution is down to tens of nanometers. This is what we're talking about in a bulk sample. Maximum size of the sample depends on your SEM, of course, but it can be 100 by 15 millimeters, for example, maximum. Angular resolution is about, in general, 1 degree for a general EBSD work, but this can be pushed down to 0.05 of a degree using these modern sort of band detection routines that are in the software. And also beyond, using to image correlation. And then we need some probe current, of course, to get some signal, and this is typically lowest quarter of a nanoamp. Usually below that, the phosphor screens aren't efficient enough. And similarly, accelerating voltage has to be high enough to stimulate the phosphor screen, so about 5 kV typically. And we need to have fairly good backscatter coefficiencies, so we tilt typically the detectors to about 70 degrees, between 60 and 75. There are detectors now that can be put at 0 tilt, but these are quite new and quite rare. Yeah, and they have, because of the backscatter coefficient, you need to use a lot of current, so you can't really get down to very low current, use them at very low currents. Working distance, of course, depends on your sample size, but it can be vary from 5 to 40 millimeters. And then speeds vary again depending on the quality of your patterns, but you can go up to 4,000 patterns or more, depending on your detector, which Jack will present what kind of detectors we have for these different kind of speeds, and also heavily dependent on your sample quality and your sample preparation. Now, for good success to high speeds, you need to have electropolished samples if they're metal. If they're not, you can only at least colloidal silica or iron beam milling, and possibly etching sometimes. So you have a polished sample, you've tilted the sample to 70 degrees, and then you put an electron beam down and you get a pattern. And then from a spot mode. And then the patterns formed by Bragg law, of course, where it forms these Kikuchi patterns. Now, if you look at alter the tilt angle, you still get a signal, but the higher the tilt angle, so I'm showing a series of tilt angles here. So backscatter coefficient increases with the tilt angle. So you can see here, for example, for silicon and iron, plots are shown, measurements as well as Monte Carlo simulations, where as you increase the tilt angle, you get higher backscatter coefficient, and you can see them also in the patterns. So, for example, at 75 degrees, you have a much sharper pattern compared to at 55 degrees. Although that's one thing that one can change the tilt angle, and you have an option to do that. But also the voltage. So the higher the voltage, the narrower the bands. But you can see the same patterns here of silicon, or is it? Sorry, this is of iron, I think, where you can see the bands are narrower. The same band at 10 kV is wider. So the interaction volume here at 10 kV is lower, but you can see that the bands are wider as well. So this can also be a bit, depending on the pattern to signal to noise ratio, can cause a problem, but also detecting these wide bands can be an issue. But typically we use 20 kV, where we get both the best of both worlds, sort of interaction volume and quality of the bands. Okay, somebody's put transact. Okay. Okay, I hope this trans works. Somebody's put that on. So detector settings also can be used for example, moving the detector in and out. And if you have a long detector distance, that means you've not put the detector far enough. You don't capture as much the pattern, but you get really wide bands for angular accuracy. And if you move the detector in, you capture more of the pattern. So you can see here more zone axes of this sample. But the bands are narrow. Now, the other thing about the tilt angle to consider is that at 70 degrees, for example, this aspect ratio of the beam is 3:1. So as you increase the tilt angle, this aspect ratio increases, and it affects the resolution, of course, in the y direction. These this is a disadvantage, but the advantage is, of course, that you get higher backscatter coefficiency, but also because you've tilted, your signals coming from the base surface, so your resolution in depth-wise improves, but in Y reduces. So there are sort of advantages and disadvantages, and it's up to you to judge which is more important when you're doing your analysis, whether tilting a little bit less might be better to resolve the resolution in Y or not. So to do the analysis, we have a software I'm showing here, because most of our systems are from Oxford Instruments, but there are different commercial softwares to do for this. This is a screenshot from AZtec to show that once you get an image from the SEM, you can put a point down and gather a pattern which you can use for to solve it when you put the what phase that is in there. So you can index the pattern using the half space, so defining the bands and the different routines for this. And this is usually a very fast process. So although there is a limit to the band detection, the detector, but the indexing can be quite fast. It's possibly hundreds of microseconds. So we find accuracy is one way to do the band detection and indexing, which is in the software. It's the most accurate way to do this, and it's typically below 1,000 hertz. I think the softwares Jack may correct me, it might be a bit more than that now, since they've made the software improvement. Optimized band detection, which was formerly known as TKD optimized, is much faster indexing, but still good accuracy. It's not just for TKD. If you're using the older version, which is called TKD optimized, it's actually for any EBSD work. And then there's standard band detection or optimized EBSD in the older software versions. And this is to achieve really high speeds, maybe not so accurate, but really high speed, because it's got minimum interaction with the band detection, so calculation time. So once it's indexed, it can give you a phase and orientation, and you can also use EDS at the same time to gather chemistry. Another way to use the detector is to get the sample, a thin sample, into a geometry where you can get a pattern, as shown here. So it's got to be thin, below 150 nanometers typically. And then you need higher KV this time, as much as possible, to go through the specimen, and then reasonable current to form a pattern. And typically the information comes from the bottom of the sample, so the exit side. And then you can also do EDS at the same time and do this. But because the interaction volume is so low, because of the thickness of the specimen, you can achieve really high resolution. So that's, if you don't need the resolution, you shouldn't really use this technique, because it is much more elaborate. But here, for example, is a nickel sample, which is done at 2 nanometer step size. This scale by is 100 nanometers, and you can see zoomed in here, we can actually we've indexed and identified 12 nanometer grains. A new another development recently is fairly recently is pattern matching or dictionary-based indexing, which is based on simulated spherical Kikuchis that I'm showing here, simulated patterns which are compared to EBSP patterns. So these simulations are many beam dynamical simulations, and an example is shown here of a spherical Kikuchi at the left-hand side here from a nickel at 20 kV, and then on the right-hand side, bottom image shows a simulated EBSD pattern from gallium nitride at 20 kV and the same orientation of experimentally of the same gallium nitride 20 kV. You can see the similarities. And so if you can use this to really get really high resolution, angular resolution EBSD analysis, and sometimes also extract more from a pattern if it's a poor pattern quality. So I want to move on to the analysis. So one of the softwares we can use is AZtecCrystal, which is from Oxford Instruments that we have abundantly here in Manchester. And we can show maps, we can clean the maps, we can do grain size analysis, we can do parent grain analysis, texture analysis, but as well as that, we can do materials properties, for example, Young's modulus, and dislocation analysis, which I'll briefly explain a little bit. So this is a typical map. You can see here where we can see the IPF colors. That means red is 001, blue is 111, and green is 101. This is of a bronze sample, so you can see these green ones are of lead actually, which are oriented in the 101 direction, their poles in the Z direction. But there's a grain here which is fully, you can see here, more of a red color, but then you can see the twins, micro twins in it in green. As well as that, you can export all the data that's gathered in Euler angles. You can put them, display them as per phase. For example, this is a stainless steel, dual phase steel, I think, where we've got the austenite and ferrite in there, and then you can see the band contrast value and the phase map. We can also look at the misorientation between data, and you can see that, for example, in this sample, there is 60 degrees around 111, which are displayed here in red, and also shown here. So these are twin boundaries in the austenitic structure. So we can use those misorientations to look at dislocation densities, because a curvature is in the lattice is formed by accumulation of dislocations, and these can be calculated how much dislocation would lead to these, and those are known as geometrically necessary dislocations. And here's a map which was calculated by John Wheeler, where he's showing the color codes of density of the dislocations, but also the arrows, the weighted Burgers vector. So he accumulated dislocations. Where is the general direction of the Burgers vector? And we've used this also to look at the deformation of nickel in situ up to strain of 8%, where you can see here, as we deform the material, dislocation density increases in the material. And Jack will show briefly what sort of capability we have in Manchester for that. And also we can do the texture analysis, show them in scatter plots or counter plots, where we can see here that it seems as a scatter plot that we have all sorts of orientations there, random, but then when we contour it, we can see that mainly we have the 01 and the 111 orientations in the Z direction. And you can also analyze ODF from this orientation distribution functions, which is much more common in texture analysis of rolled sheets, for example. It's more common to use this. There are some references that I'm going to give, for example, the Bunga book and Cox on texture analysis, and Valerie Randall's book on texture analysis. If you want to look at basics of ABSD, Schwartz's book on that, which is a compilation of papers, is a good one. And F.J. Humphrey's book on recrystallization and related nonlinear phenomena is a good one to for material scientists to talk about, which talks about texture. So finally, I just want to, before handing it to Jack, I want to say that the if you want to access the AZtec and AZtec crystals offline, it's possible. You have to install the latest version and set up the IP address for the network server at Manchester. And if you want further details, get in touch with Patrick Hill, Jack, or myself. So that's as much as I wanted to talk about to you about, and I want to hand over to Jack for his part of the talk.
Thank you very much, Ali. Right, so let me just see. Share my screen for the moment. So here we are. Right. So in Manchester, in the EMC, we are very lucky in the number of machines we have. We have 14 systems in total that are capable of doing EBSD, and they are split pretty evenly across our two sites. So this is a little bit ahead of ourselves because some of these systems are still either being commissioned in MECD or moving there, but in a few months' time, this will be accurate. So yeah, 7 systems in MECD. That's where we've got the more general use microscopes, and we've got 7 systems in PSI, where the generally more specific ones. In MECD, you will also find the EM sample prep labs for the iron polishing and things that really do help get samples for EBSD. So we have 3 different detector types in Manchester, all by Oxford Instruments. We've got quite a few of the previous generation of detectors. So those are the Nautilus series. And we have 2 different types. We have the sensitive detectors and we have the fast detectors. So with the sensitive ones, you generally need a smaller probe current in order to get good patterns. So you get more resolution, but it also allows you to work on some more difficult materials. With the maxes, you sacrifice that sensitivity for going fast. So that's particularly useful for 3D studies. And in the last few years, as Ali was saying, the CMOS-based detectors, the symmetries that have been released. And with those, you kind of get the best of both worlds. You can use them in a sensitive way, although I'd still argue that the Nautilus S is probably still slightly more sensitive than the new detectors, but you can also operate them in a fast way, very fast. So we are getting up to 3000 hertz or maybe 4.5 on some of the S2s, but yeah, the sample has to be right, single phase, large grains helps. And this is the distribution of the microscopes and where they are and what they're on down the side. Okay, cool. So I'm going to talk about some of the more specialist techniques we also have available to us. So there's large area mapping, simultaneous EBSD and EDS, which Ali has touched on as he did with TKD. I'm also going to show a little bit on the serial sectioning and the in situ experiments. So large area mapping. So rather than keeping the stage in a single position for an EBSD, where you are limited a little bit by your view field, although typically in a single map, we would go smaller than the lowest magnification of the microscope due to distortions at the edges. So we will go for smallish view field, maybe 500 microns, and then automatically move the stage while mapping in order to do a large area. So in this sample, I have my Lego men for scale. So this sample is around about 10 centimeters wide and about 6 or 7 centimeters high. This doesn't quite do it justice, so I have loaded up the image here so you can really see the advantage of the large area mapping, because this map has got lots of tiny recrystallized grains along the grain boundaries. This map is enormous, but with the new detectors, it didn't take that long to collect. It collected in about 24 hours. Right, back to the presentation. So we have a number of systems that it's capable to do simultaneous EBSD and EDS, and this is a list of them in appropriate order of capability. So at the top of the list, we've got our Zeiss systems that have got very decent EDS detectors, well tuned to the working distance that we collect EBSD on these systems, and you can get some very nice simultaneous maps. And at the bottom of this list, we have the systems that are better suited to other things. They were bought as FIBs for serial sectioning. So if you're wanting to do simultaneous EBSD and EDS, you'll have to justify these. And down here, we've got the detectors that they're paired with. So sensitive is the Nautilus Nanos, and the speeds would be the maxes for the large area. TKD, as Ali was saying, we can do this for increased spatial resolution and can be combined with EDS. He showed a much nicer example of this than me, but my one does have some EDS on there. So you can see that we were getting some EDS resolution in the kind of tens to hundreds of nanometers, which normally you would not get in an SEM at 30 kV. Of the systems we have, the Merlin and the Magellan probably top the list, quickly followed by the Sigma. But any microscope with an EBSD detector can do TKD, but I would definitely kind of push towards those three as the better systems we have. 3D capability. So we have a number of FIBs that are capable for 3D studies, and the volume investigated generally scales with the material removal rate of the system you're using. So the gallium FIBs have the lowest removal rate, so you're typically looking at doing regions of 20 microns by 20 microns with very small voxel sizes, and so you can tailor your study to which system you're using. As we move towards a xenon FIB with a larger ion, our material removal rates jump up by roughly an order of magnitude, as does the area we investigate. We could look at a smaller voxel size of that, but then the time of investigating such a large volume with a small voxel size basically makes the study undoable. And we've recently received this femtosecond laser system, which again, another scale up. So we are now able to investigate 500 microns by 500 microns. And here is a data set that we collected not that long ago. So this was in aluminium with a 600 micron slice, and we managed to do quite a large block. And I think we did that with a 1 micron voxel size. Oh, and at the bottom here, I've just tacked on that we have another 3D EBSD available technique, which is a broad ion beam that we have attached to the NOVA. So that is a little shuttle technique that takes the sample out, gives it a quick broad ion beam polish and puts it back in. The advantage being that you can mill away a very large area with a very high Z resolution. So just removing a few nanometers at a time, and then target particular features with which to do your 3D EBSD studies. And finally, and this is my kind of bag, I like my in situ studies, partly because it means I get to put together nice little animations, is in situ work. So these days, this is mainly taking place on 2 microscopes we've bought solely to do in situ studies, and we've only recently moved towards integrating EBSD with those. So this can be EBSD with strain, which is what I'm showing in the animation on the left. So this was a copper sample that we took up to quite high strains and EBSD'd every few steps. And on the right, this is with temperature. So this is a titanium sample held at 1,000 degrees. In the corner, you can see the little time ticking away. And this is the beta grain growth in it. Up until very recently, this was all done kind of semi-manually. So we would apply a strain step and then a temperature step and take a map, another strain step, another map. But we are moving into automating this. So with the hopes to kind of run it over the weekend and collect far more temporally resolved data. Finally, I'm going to leave us on a GIF that I haven't integrated into the presentation because we only acquired it last week. And this is fairly novel because this is EDS at high temperature. So here we have simultaneous EBSD, EDS with high temperature. We go up to about 880 degrees. In this top left image, we can see the beta grain growth, especially in the left-hand corner. If we let's see if it lets me look. We watch this orange grain on the very left of the screen. As we go up in temperature, the beta grain shoots across and gets it. And then as we cool down, the iron kind of diffuses back out and enriches the other phase. So we've got the HCP phase, the BCC phase in a nice little loop. Cool, I'm done. So I think Ali and I are now opening the floor to questions.
Yeah, thank you very much, Jack, for that lovely presentation. Very nice slides. I really liked the movies too. Thank you for that effort to put all this together in a short space of time. So yeah, excuse me. As Jack mentioned, the floor is open to, well, Zoom's open to
there's
questions.
a question in the chat. How long do you spend on your large sample scanning?
So in the case of that large map that I showed, we had a glitch with AZtec at the time, so it took longer than it should have. But if it took as long as it was supposed to, if AZtec was working well, it should have taken around about 24 hours.
Yeah.
Thank
So
you.
with our fast detectors, that's quite
yeah, well, it's one of those that we get down to how much data is too much data. So we can only stitch a data set together if it has fewer than 64 million pixels. But if you think about 64 million pixels, that's an awful lot of data. You're going to struggle to analyze that. So sometimes bigger isn't better. And when you get onto these very large areas, what is limiting you isn't necessarily your detector speed, because so much of the mapping time is taken up by stage movements. And that becomes a big factor in any of these scans.
Yeah, and also the practical aspects of it, I guess, just to, you know, setting up such a system is much more difficult than just normal EBSD maps. So yeah, it takes a bit of geometry-wise to make sure that you don't collide with anything. But generally, I think, yeah, as long as you have a single phase sample, it's easier to do, much faster, I guess, than if you have a much more complicated sample. Yeah.
Yeah.
I think there's a question about how do you prepare that. Maybe before we move to a different topic, do you want to explain how you prepared that sample?
Well, I didn't. Someone else did. So I find that's always the easiest way to get good sample prep done, is to rely on others. That was a sample prepared by a chap at Strathclyde University. And I asked him about his sample prep, and I think the answer was just effort, time and effort. But yeah, I mean, there were a few scratches on it, but to prepare a sample that's 10 centimeters into, and it was so flat, he did a very good job.
Thank you. Ellen has asked whether TKD of twisted 2D materials has been reported, to your knowledge.
To my knowledge, I haven't seen any 2D materials. Of course, what it is an interesting topic, I must admit, but it's a matter of getting the EBSPs out of it. Usually you need some interaction volume. So if you make a sample too thick, then you don't get enough signal and you actually get a reverse contrast in your pattern. And if you go to thin enough, then you start getting a really nice Kikuchi pattern. But then if you go too thin, you start getting reversal again. And gradually the signal drops because there's no interaction. So I haven't seen any, and it would be nice to try, but I would it wouldn't be so trivial because, as I say, the signal would be I expect to be very low because of the very small interaction for diffraction form.
There's a question about how is the calibration of the detector confirmed? Say the sample is tilted to 70 degrees, do the dynamic tilt correction, And it says, and our observation is from the point of view of the detector camera. Could you elaborate on this a bit?
So I'll start, maybe Jack can fill in. So the calibration of the detector is done by the engineer. So you don't need to really start from scratch. So what happens is that when the detector is installed, the detectors move to several different physical positions in space with respect to also the sample moving, and that whole space is captured in a database. That's used as a calibration basis, so that when you click on a point, and the software reads the SEM working distance, the detector position, distance, so forth, and then based on that, the pattern center, which is known as the from your the point the beam hits the sample, normal to the phosphor screen, is the pattern center. That position is accurately sort of defined in space, and that's used as your calibration. So you don't normally have to worry about that. But what you can do is you can refine this calibration. So, for example, if you're at 19 millimeters, but actually your distance is 19.06 millimeters, then there is a button in refine, and you have to make sure that your band detection is perfect. So you've got good quality patterns. To then, when you index, you can refine that solution, and that refines the calibration. So as a user, you can refine the calibration.
So that's Optimized Solver, and we kind of go through that on one of the videos that we put out there. So yeah, watch through those. We'll send out the links afterwards in the Slack group. But so I would always trust the EBSD detector calibration, especially if we're doing this, because if it's not well calibrated, if it's got it won't index anything. It'll get it very wrong. The thing that I would never trust being as well calibrated is the position of the beam. You can be confident in how the pattern has been indexed, but the position of the beam can be more worrisome, because so you do a 70-degree tilt correction, but that is under the understanding that you have definitely got your sample nice and flat with what's there. And is your sample truly at 70 degrees? Or have you got a 1-degree angle, so you've got it at 69? In which case the tilt correction won't be positioning the beam in the correct place. So you've got to be very careful about how the microscope has stretched your image and distorted it, because that won't always be perfect. But I would definitely trust the EBSD to give you a good orientation for the position that it's interacting with.
Very good point. So that brings a point that you have to make sure that your samples are not just flat, but horizontal. So when you say samples have to be polished flat, some people just think, okay, it's got to just be have a very smooth surface, but that's not sufficient. You also have to have a horizontal. So your parallel between bottom and top surfaces are parallel. If they're not, the problem that Jack mentioned becomes a big issue.
Thank you for that. Another question: what is the maximum temperature that in situ EBSD can go to?
Currently, we have done maps at 1,000 degrees, and we can do maps at 1,000 degrees. I wouldn't generally like to do maps at 1,000 degrees for a particularly long time, or if I am to do that, as part of the study, we will consider the phosphor screen as a consumable. The infrared radiation does have an effect. So at 800 degrees, I'd be happy leaving it for several hours, and that time deteriorates with the higher up in temperature we go. So we can do EBSD at 1,000, but for less time.
Yeah. So when you increase the temperature, what happens is at about, I would say, 400 degrees centigrade, you start getting some infrared radiation, which is basically light emitting from your sample, basically glowing. When you have a piece of iron and then you put it on the hot flame, it turns into red. That's basically infrared. And that actually causes problems in the EBSD, but we have filters to deal with that. So in the detectors, in the modern detectors. So that's also a limiting factor when infrared starts forming, infrared radiation. But then there are mitigations for that in the modern detectors that we have.
Thank you. Another question, is it possible to do in situ EBSD for samples that react when the temperature increases?
Well, unfortunately,
react.
all sorts of things happen at surfaces when we're at high temperature in the SEM, and very often we don't want them to react, but they do. So we're in a high vacuum and we try to eliminate the oxygen as much as possible, but you can still sometimes get oxides forming. And when they do, that does prevent any patterns. We are a very surface sensitive technique. So if you are looking for something to happen on your surface, we can do it on purpose or we can do it by accident, but never combined with EBSD because it prevents you. Any reaction product you get on the surface will prevent patterns escaping.
Yeah, I agree. And also, that's a very important point to consider before doing any in situ high temperature work, is to think about reactions. And if you look at phase diagrams, for example, of a binary alloy, usually a eutectic, has a lower melting temperature. You don't want your sample to melt inside the chamber and cover it all. So your analysis has to be thought out really well before it goes into the microscope. So it's not just let's stick it in there and try it, because you could damage a £1 million machine, make it worthless if you don't think these through.
Mm-hmm. There's another question. I don't know what fibers we're talking about, but it says, can EBSD be applied to twisted fibers, 20 microns, to study their in situ heat and moisture transfer processes? I don't think.
I'm not sure if I follow on that one, but
no, I don't.
Yeah, I mean, we study crystallography, so we are not
fiber
their heat transfer.
Well, I suppose it depends what the fibers are. Henry, do you want to come on and ask your question?
Yes, the fiber could be like a graphene fiber or graphene oxide fibers.
Okay.
Yeah, again, this is a very good question, but similar to the initial about 2D materials. I think one of the things is, of course, look at crystalline material, although graphene is crystalline, and you get diffraction patterns in a TEM. But in an SEM, what we're looking for is Kikuchi patterns, not just diffraction patterns that you see in the TEM, the spot patterns. And for the Kikuchi patterns to form, you need certain volume. So you need the lattice to the electrons to interact with. And one layer graphene is unlikely to form a Kikuchi pattern. But if it's a several layer graphene, so basically graphite, it may do, but I must admit I haven't seen one yet. So if we're just talking about graphite, but if it's something that's going to be dehydrating, losing water and so forth, well, then is it crystalline? You have to consider these things, and also what's it doing inside the chamber? Is it causing any problems in there? So a lot of things may be in theory possible, but in practice it may not be applicable because of the limitations of our equipment.
Okay, thank you. By looking to your presentation, you did mention a temperature can increase up to 1,000 degrees, which is it means since the detector actually within the chamber, which the chamber can change the environment. Is that correct? You have an environmental chamber.
We do the experiment in a VP chamber, but we don't do it under. But where we can test under different environments. Generally, we've only tested under pressure up to about 500 degrees, because what you want to avoid is convection of heat around the chamber. But generally, these tests take place under high vacuum. However, I see that we are getting on in time a little bit. I think we've hit the 3 o'clock mark, which means, unfortunately, Evan, we're not going to get onto your ridiculously complicated question.
I'm glad you said that. I was thinking, am I going to say all this?
Yeah. No, sorry, Evan. But I would say that I am aiming to be at the coffee morning tomorrow morning. So
Cool.
if anyone has any more very specific questions, I can pretend I know the answers there.
That's fine. Just quickly though, can I ask, is there any low acceleration voltage limit for EBSD?
5 kV is generally the limiting point. Below that, you're not going to get fluorescence of the phosphor screen. But yeah, it's about 5 kV.
That kind of answers my question, really. Like 2D materials, you need to go down to 1.5 kV anyway. So yeah, that's okay. Thanks.
Well, I'd just like to say thank you, Ali. Thank you, Jack. Really good talk. Thank you very much.
Cool.
Yeah.
Thank you, Mike. Thank you for fielding the questions.
Yeah.
Thank you.
And thank you for everybody attending. I hope we can do this in person soon.
It'll be good.
Take care, all.
Yeah, take care. Thank you very much.